Okay. So yesterday we spoke about a little bit about calorimetry. We did some enthalpy calculations as well. We'll come back to enthalpy, I guess, today. But let's take a look a little bit more at calorimetry. And we're focusing primarily on constant pressure calorimetry. So the idea is that the heat of reaction, or delta H, the change in enthalpy, is equal to the amount of heat either absorbed or released. Now, most of the examples we look at are released exothermic, but there are some reactions that are endothermic as well. So Q sub P, meaning that this is done at constant pressure. So if it's not done at constant pressure, you can't use that relationship. You have to approach the problem a little differently. But what we said yesterday was that there's a way to figure out what Q is. So Q is equal to MC delta T, where delta T, well, let's write it out. M is the mass of the substance changing temperature. So typically that's the water, the solution that you're running a reaction in. C is called the specific heat capacity. And that refers to that substance that we're talking about with the mass, the same substance, okay? So most likely the water. Specific heat capacity. And then we have delta T, which is the final temperature minus the initial temperature, again, of that substance that's changing temperature, okay? So typically, we can find specific heat capacities in some table of values. We can measure the mass of a substance pretty easily. And then if we have a thermometer, we can measure the temperature and get the temperature change. So we can calculate delta H out of this, actually. It's kind of cool. So let's take a look at an example. The one we looked at yesterday was a little different. It was where you had to find the specific heat capacity given the amount of heat that was added to the system. But now we'll look at an example where we are using the specific heat capacity. And I'm just going to call it specific heat instead of specific heat capacity to find the temperature change. Okay, so let's take a look at this example here. The example is they tell you there's a chemical reaction occurring inside a flask that's submerged in a water bath, and that the water bath has 3.50 kilograms of water. Okay, so let's draw a little picture of what's happening here. We've got a water bath. Remember, the water bath is insulated. It's like a thermos. And that's just to slow down the transfer of heat from the water to the surroundings. Because if the heat goes into the surroundings, meaning, into the air, that's going to reduce how much temperature change you get with the water. Remember, it's the heat that causes the water to change temperature. So if some of that heat is lost to the environment, you're going to underestimate how much heat was produced because the thermometer in the water is not going to measure that as well. So we have a thermometer. Okay. So you got some kind of liquid inside the thermometer that rises as the temperature increases. And then we've got a water bath, right? So there's water in here. H2O. Okay. And then it says there's a flask that's submerged. So what's interesting about this is we don't need to have the thermometer in the flask. And the reason for that is the flask is going to allow heat to transfer back and forth with the water. So it's just more convenient to measure the temperature change in the water. Plus, we know the specific heat capacity of the water, right? It's 4.184 joules per gram degrees C. So we've got that value. So let's take a look at the numbers that are given here. And this is constant pressure. It's open to the environment. So we have the water bath has 3.40 kilograms in the water bath. So that's, well, yeah, that's like 10 pounds or so. That's quite a bit, right? 10 pounds of water. Well, not quite, about 8 pounds of water. And the temperature, so this is at 37.6 degrees C. That's not too far off from the temperature of humans. Okay, so during the reaction, (66.7 kilojoules of heat flows out of the flask. And into the water. Okay. Into the bath. They actually say the bath. It's the water bath. Okay. So calculate the new temperature of the water bath. Okay. And then they tell you to assume that the specific heat capacity of water is 4.184 joules per gram degrees C. So here's the approach. We know the initial temperature, right? The water is at this temperature. Heat flows out of the flask and into the water. So that reaction is exothermic, right? If heat is flowing out of the flask and into the water, the reaction is occurring in the flask. That means that the reaction is exothermic. It's going to heat up the water. We also know the mass of the water, right? There's a mass of our water. Okay. So here's what I'm going to do. I'm going to calculate Q equals MC delta T. Okay. Now, since they're asking us for the final temperature, they don't explicitly call it the final temperature. They say the new temperature, but the new temperature would be the final temperature. It's useful to write this as M times C times T final minus T initial, because we have to find one of those temperatures. Okay. So here's what I'm going to do. We need to find this final temperature. So we've got to algebraically isolate TF. So here's what I'm going to do. I'm going to divide both sides. So over here on the left where we have Q, and over here where we have MC, T final minus T initial, I'm going to divide both sides by MC. Okay. So M divided by M is 1, and C divided by C is 1, right? So now we have Q over MC equals T final minus T initial. Let's write that over here. Q over MC is equal to T final minus T initial. We don't want to find T final minus T initial. We want to find T final. So what do? We need to get the T initial on the other side, right? So we add T initial to both sides. So see what I'm going to do here? Plus Ti over here, plus Ti over here. Because if you add T initial to the right side, those two cancel, right? -6 plus 6 is 0. So those are gone now. So now you've got T final. So our calculation here is T final is equal to T initial plus Q over MC. Okay. Okay, hold on 1 second here. Let me just do a little something. Sorry, just 1 second. Okay. All right, so let's go ahead and put those numbers in. T final is equal to T initial. So our T initial is 37.6. So let me just write that over here. T final is 37.6 degrees C. Plus, now we have Q, which is 66.7 kilojoules over MC. So M is 3.40 kilograms. And then we already know what C is. It's 4.184 joules per gram degrees C. Okay, so take a look at what happens to the units in that second term. Everything in the end should be in degrees Celsius, right? If you're calculating a temperature, the units should be temperature units, right? So we have kilo cancels with kilo. We have grams divided by grams. We have joules divided by joules. So all those units cancel with the exception of degrees C. And so really it's 1 over degrees C, right? Because this is the numerator here, and then degrees C is in the denominator down here. So it's like a compound fraction. So 1 over degrees C is just degrees C. So there's our answer, degrees C. So that's good. So we can add degrees C together. So let's go ahead and run through the calculation there. We got 66.7 divided by 3.40. Oops. 66.7 divided by 3.40 divided by 4.184. So 4.6887 is what I get for that. So we'll just add that to 37.6 and you get 42.28887. Oh my. So I'm just going to round that to 42.3. Okay, I rounded it to a tenth into the tenths column because this one only goes into the tenths column. So even though we've got a lot of numbers here, we're going to round it to the first digit past the decimal point, which is the tenths column. So it went up, right? It went up to 42.3. That kind of makes sense because if heat is going into the water should get hotter, right? So there we go. Notice with the units, this was in kilograms, this was in kilojoules, so the kilos canceled. So there was no need to do any unit conversions to convert it to joules or to convert it to grams. So just a little analysis of that or taking a look at it can help you with that. Okay. All right. So let's see. Okay, so let's take a look at one that's related. This one's called calculating the molar heat capacity. Okay, now you're going to see this term in chemistry, molar. You've actually seen it already with molarity, right? Where you take the number of moles of something and divide it by the volume to get the molarity. But let's take a look at one that's a little different. So this one says that where a chemist is carefully measuring the amount of heat needed to raise the temperature of 0.64 kilogram sample of C6H7N from 26.2 degrees C to 40.7 degrees Celsius, right? And the experiment shows that 2.00 times 10 to the 4 joules of heat are needed. Okay, so that's how much heat is needed to raise the temperature from 26.2 to 40.7. What can the chemist report for the molar heat capacity of C6H7N. Okay, so let's talk a little bit about what the molar heat capacity is. That's a new term, right? So we're familiar with something called the specific heat capacity, right? That's the C. The specific heat capacity in units is the number of joules required to heat a certain mass of something in grams, a certain temperature. So imagine it this way. Imagine that you said, hey, I've got a bathtub full of water, and I'm going to add some heat to it, right? How are you going to add heat? Well, you could put a little flame underneath it and add some heat to the water, okay? So you're adding heat. That water has a certain mass, and that mass is typically in units of either grams or kilograms, okay? And it has an initial temperature and it has a final temperature, right? So it has a delta T. So what is the specific heat capacity? It's the amount of heat that you're adding, right here, divided by the mass, how much water you have, divided by what the temperature change is, right? That's really what it is. It's the amount of heat you add divided by the mass divided by the amount of temperature that it changes by. So if it went from 10 degrees C to 30 degrees C, it went up by 20 degrees Celsius, okay? That's what the specific heat capacity is. The molar heat capacity is the same thing. So I'm going to write it as Cm for molar is really equal to the amount of heat, joules, but now we're going to divide it by the number of moles of the substance and then divide it by the temperature change. So in other words, it's Q, not divided by the mass, but divided by the moles of the substance, and then times delta T, okay? And that's not a difficult calculation for us to do because we know how to convert the mass of something into the moles just dividing by the molar mass, right? So if we know the molar mass of the substance, we can do that. So all you need to do then for this one is instead of putting in the mass, you put in the number of moles here, okay? Now I'm going to write it as a little differently. I'm going to write it as Q divided by N times delta T. So N, we're going to use that symbol for moles, okay? And if you actually go online and you start looking up heat capacity, heat capacity, heat capacity, what you'll find is that sometimes it's done in terms of the molar heat capacity, not in terms of the mass, the specific heat capacity. Specific is mass. Molar is you're dividing by the moles. Okay, it's simple. It's that simple. So if you think about it, they gave us the chemical formula and they gave us the mass. So if you have the mass in the chemical formula, you can find out how many moles that is, right? They gave us delta T. We know the initial temperature and the final temperature. Initial's up here, right? Final's down here. And then they gave us the amount of heat. So we've got everything we need. We just need to figure out how many moles that is, okay? So let me make a little room over here. And, you know, molar heat capacity is pretty common. It's not as common as specific heat capacity, but it's used quite a bit. So let me just go ahead and do this. So molar heat capacity would be Q over N delta T. Okay, so let's put in the numbers that we have that are very simple. We know the amount of heat, 2.00 times 10 to the 4 joules, right? That's simple. That's given. We don't know the number of moles yet, so I'll put that in parentheses here. But we do know we do know both of the temperatures. We know the initial and the final. So remember, it's final minus initial. So 40.7 degrees C minus 26.2. Okay. And that'll give us our answer. So we just got to figure out how many moles there is. Now be careful, this is in kilograms. So we have 0.64 kilograms of C6H7N. And we need to figure out what its molar mass is and then convert that into moles. But it's in kilograms. Remember, molar masses are in grams per mole, right? Not kilograms per mole. So let's do the following. Let's do the conversion. 1 kilogram is 1,000 grams. So that means 0.64 kilograms. 1,000 grams is a kilogram. So you get 640. So now we have the number of grams there. So now let's figure out what the molar mass is. There's 6 carbons. So 6 carbons, 6 times 12.01. Units of molar mass are grams per mole. There's 7 hydrogens, so 7 times 1.01. And then 1 nitrogen. And there you go, okay? So 72, 79, 89, 93. 93.0, was that 1314 grams per mole. Okay. So there is our molar mass. It looks like it's aniline. Let me see. I'm sorry. Sometimes I have my own curiosity. I have to do these things. So it looks like it's 1, 2, 3, 4, 5, 6, 7. Okay, so there it is. That's aniline. Okay, so now we have 640 grams. So we're going to just divide that by the molar mass, right? So 640 grams, and then it's 1 mole per 93.14 grams, right? Just dividing by the molar mass to get the number of moles. So 640 divided by 93.14, and it looks like you get about 6.871. Keep 1 extra sig fig, and there's your number of moles. Okay, so we're almost there. Well, let's just put that in there, 6.871, keeping 1 extra sig fig. Okay. Now we just do our division. Let's do the dimensional analysis. Let's just make sure the units work out. This is the molar heat capacity. So molar heat capacity should be in units of energy, which in this case is joules, divided by moles. That's how it should work out. So let's see if it does. Oh, I'm sorry. It should be joules divided by moles divided by degree C, because it's the heat capacity, right? So per degree C. So it looks like we got joules here. It looks like we got moles here. We got degree C. So that looks good. So 2 times 10 to the 4 is 20,000. Divide that by 6.871. Divide that by, let's see, what is that temperature? That's 14.5. So it looks like it's about 200. Now, actually, it's 200.7, but we're only justified in putting 3 significant figures here. All the numbers have 3. So let's round it to 201. And so that would be joules per mole degree C. Okay. Now, this is a little tricky in terms of interpreting the result. And the reason that it's tricky is because what I told you yesterday is that typically, we said that metals have specific heat capacities of less than 1, and then water is very high at 4. So you're not going to expect things to have heat capacities greater than 4. But that was specific heat capacity. This is molar heat capacity. So the molar heat capacities are higher. They can be in the hundreds. So specific heat, metals less than 1, non-metals greater than 1. Molar heat capacities are going to be in the hundreds here. Okay, so there you go. So just be careful with that. All right, so that's called molar heat capacity. Molar is something we do quite a bit in chemistry. I would probably argue that the specific, so there's something called specific gravity, which is a measure of your density, specific heat, which is a measure of the heat capacity. Those are typically per gram, dividing by the mass. But these days, it's more frequent probably in chemistry to use molar quantities, so per mole. So molarity, molality, molar heat capacity, molar volume. That's just more common. So that's why that problem's in there. Okay. Okay, let's see here. We got one more. Okay, we got one more calorimetry problem to do, which they call a basic calorimetry problem. So it's called solving a basic calorimetry problem. Okay. So in this one, they give you a constant pressure calorimeter, insulated container. They show you the picture of it. It's very similar to the one we've done. So let me show you the picture here first. I'll draw the diagram. So again, you have an insulated container, a thermos, to slow down the heat. Now, if you have a container that's really, really good and keeps the heat from transferring out, at least over a long period of time, we call it an adiabatic system. So adiabatic means there's no transfer of heat from the bath to the environment. Okay. That's also called a closed system. You'll see that term too. Same idea. That essentially, closed system is there's no transfer of matter between the bath and the environment. That's called a closed system. And then an isolated system. There's no transfer of matter or energy, neither one, or heat between the bath and the environment. Okay, so if there's no matter or heat, neither one of them transfer, we would call that an isolated system. So typically adiabatic systems are isolated systems. Okay. So that's just some terms you should be aware of. Okay. So there's a little object that they put in here. So we'll put that in there. Of course, we have a thermometer. This is a water bath, right? So there is a lid. The lid would be, typically the lid would be kind of loose fitting so that the air pressure can regulate. I mean, the air pressure can equilibrate. The term is equilibrate, be the same as the pressure of the air inside the container. So we're going to have a little thermometer. That's going to measure the temperature. And then inside, okay, it's water, right? This is a water bath. Okay. So this is a little bit different than the one we did before. We're not putting a reaction in there. This is just some sample, something we're throwing in there. It's not actually chemically reacting. All it's doing is just transferring heat because it's either hot or cold. So remember, heat moves in the direction. There's a directionality to heat. Heat moves from the material that's higher in temperature to the material that's lower in temperature, right? So if it's hot outside and your window is closed and it's cold inside, what happens? If you open the window, it gets hotter on the inside, right? That's because heat is being transferred from the hotter region, which is outside, into the colder region, which is inside, right? I had a family member when I was growing up as a kid who would say, you know, while we were driving a car, they'd say, don't roll down the window because you're going to let the cold go out. And that's not actually how it works in nature. Cold doesn't go. It's not the movement really of cold. It's the movement of hot. So heat flows from higher temperature into lower temperature. There is no actual quantity called coldness, right? Coldness is a lack of energy. Hot or hotness is the presence of energy, okay? So now let's get to the calculation. It says that this material is brass. So that's a sample of brass. So I'm going to write that down. We may need to know what the material is if we need the specific heat capacity. So we could look that up. I think I mentioned yesterday that if you look in a physics textbook or an engineering, they will have a table of different materials that you can look up the heat capacities or the specific heat capacities. Chemistry textbooks usually only have a few materials, pure substances like copper, water, but brass is a mixture of different metals. So you'll find that in an engineering or physics book. But for this one, they actually give us some information. They say it has a mass of 53.5 grams, and they say it has a specific heat capacity of 0.375 joules per gram degrees C. Okay. So what they do is they say you're going to put that into the calorimetry. Remember, this is water here. And it has 300 grams of water. So let's write down our information about water. 300 grams. Actually, it's 300.0 grams, but I'll ignore that for now. And remember, we also know the specific heat capacity of water. That's one you might even want to memorize, 4.184. So we got that. So the temperature of the water, it tells us, is 22.0 degrees C. And then they say when the water is done changing temperature, its final temperature is 23.1. Now, I went through and kind of interpreted everything that they were saying in that problem and writing the numbers down. Obviously, that's something that you're going to have to do yourself. So that's a challenge when you do these problems, right? Part of what we're learning to do in this course is problem solving. So I wrote all the numbers down here, but you're going to be reading through that paragraph and then kind of writing those numbers down. But this one's actually pretty well written. It isn't complicated. It's not that difficult to tell which the initial. It says it started off at 22.0. It said it's the water. So all that information here is about the water. So it's actually a pretty well written question. Not that much interpretation here. So there's your water. And then here's your brass, right? Now, we have to figure out what's the question going to be, right? So the questions can vary. So what it says is calculate the initial temperature of the brass sample. So what it says is calculate the initial temperature of the brass sample. Cool. Cool question. All right. Here's how we're going to go about doing this. Okay. It's a little different than the ones we've done before. Essentially, what is occurring here is if you take a look at the water started off at 22 degrees Celsius. And it ended at 23.1 degrees Celsius, right? So it got hotter, right? So that means that heat was transferred from the brass, right? The brass is transferring heat to the water. Okay. In a sense, that's an exothermic process, right? From the perspective of the brass, it's releasing heat into the water. So that means that the brass started off at a temperature that was actually greater than 23 degrees C. It had to be greater because in order for something to transfer heat to something else, it has to be hotter than it, right? So it had to be hotter than whatever that final temperature was. I'm sorry, hold on one second. Okay, so heat transferred from the brass into the water. So here's the way we're going to do this. We know that for each material, there's heat associated, right? So the brass is releasing energy in the form of heat into the water. So here's how I'm going to write this. The amount of heat that the brass releases has got to be equal to the amount of heat that the water absorbs. Again, this is insulated, so there's no loss of heat. We're assuming there's no loss of heat. So all the heat goes from the brass into the water. So here's how I'm going to write this. I'm going to write it as Q brass plus Q water equals 0. Now that might not be obvious to you why I'm writing that, but essentially what I'm doing here is called conservation of energy. What I'm saying is that in any process, we do not create energy or destroy energy, we merely transfer energy, right? So if you're at the top of the hill, remember that first problem in the chapter, you're at the top of the hill, you ride down, potential energy as you go down the hill is decreasing, but kinetic energy is increasing. We're transferring that energy into a different form, motion, right? But we're not creating energy, right? It's there. It's just being transformed. Same thing here. The heat that the brass loses, right, has got to be equal to the amount that the water gains. So think about that in terms of money again, right? I use this as a lot of times. Maybe it's not the best analogy, but sometimes people are familiar with it. Suppose I say, look, you know, you got you and you got your friend. And you say, hey, here's $100. I got $100 bill. And you give it to your friend, right? During that process, there's no creation of money, right? It didn't get printed or anything. You just gave it to someone, right? So essentially you lost $20 and the other person gained $20, right? But if you add those two together, it's 0. There's no net creation or destruction of money in that process. So the same is true with heat. The brass gives energy in the form of heat to the water. It loses it, the water gains it. So one way to do that mathematically is to say, you know, minus $20 plus $20 equals 0. And that's exactly what we're doing here. We're saying the heat that the brass loses plus the heat that the water gains is equal to 0. So the water gained, you know, we know the water gained because it got hotter. Okay, so let's take a look. Now what I'm going to do is I'm just going to write out our equations. So this would be MC delta T. So I'm going to write MB, right? B for brass, CB, meaning the specific heat capacity for brass, and then delta TB. So that's the change in temperature for the brass, plus M of the water. I'll put W for water, C of the water, delta T of the water, right? The water changes temperature, but so does the brass. Now, we know a lot of these pieces of information. They gave us these two up here about the brass, so we know these two here. We know the water mass and the water specific heat, so we know these here. We also know delta T for the water, right? We know the whole delta T because they gave us the initial and the final, okay? So let's do this. I'm going to put in everything that we know and just solve for delta T of the brass. So I'm sorry. So this is equal to 0, right? So this plus this equals 0. So this plus this equals 0. So here's what I'm going to do. We want to know delta T of the B of the brass. So we just want to know that. So how do we deal with that? Well, the first step that I would do algebraically, and I'm not going to claim this is the only way you can do it, but one way you could do it is, since we're trying to isolate this term over here first, we just need the other term, the one for water, to be on the other side, right? Because, you know, again, you're looking for something like this, y equals 3x plus 2. You're trying to find one thing and you want everything else on the other side. Okay, so I'm going to subtract MC delta T for the water from both sides. And that's going to give me MB CB delta TB equals minus MC delta T for the water. Right? Why minus? Because we're subtracting it from both sides. If you subtract something from the left side, it becomes 0, right? 6 minus 6 is 0. But on the right side, you can have minus. So you can have a minus. So don't forget that minus on the right side. Sometimes people actually write it this way. They just say, look, Q of the brass equals minus Q of the water. If you want to write it that way, you can do it that way. You're already ignoring the first step and just moving on to the second. Now what I'm going to do in the second step is I'm going to divide both sides by the mass and the specific heat capacity of the brass. So why am I doing that? Because we're trying to find temperature of brass, right? So we're trying to get everything to the other side. So if you divide both sides by M and C, you get delta T equals, okay, so minus MC delta T. This is for the water. And then we're going to divide that by MC. Okay, so that's equal to that. So we were almost there. We're not trying to find delta T of the brass. We're trying to find the initial temperature of the brass, but I'll show you how to do that. But this is kind of the first step, which is to figure out what delta T is. Okay, so I'm running out of room here a little bit. So what I'm going to do is I'm going to get rid of this discussion, this sort of side discussion of adiabatic and open and closed systems. If you have to do any engineering, you know, that whole discussion of adiabatic and open and closed is important. If you are going to take any, like, you know, any of those professional exams like the MCAT or the PCAT, they're important as well because they're going to ask you questions about that terminology. So I did want to mention it too. Okay, so I'm going to come back up here a little bit. So delta TB, I'm just going to put the numbers in now. So we have a minus. So the mass of the water is 300 grams. I'm actually putting the 0.0. The problem actually said 0.0. So I'm going to put that in. Let's use parentheses just so we can see what we're writing in here. Specific heat capacity of the water, 4.184. When in doubt, if you're talking about water, put in 4.184. And then I'm just going to go ahead and do delta T. Delta T is final minus initial. So that's 23.1 minus 22.0, right? That's over here. So that would be 1.1 degrees C. Okay. And then we're going to divide that by the mass of the brass, which is 53.5 grams. And then the specific heat. Remember I said in terms of, you know, per gram specific heat, metals are less than 1. So here's a good example of that. It's actually pretty close to copper. Copper is 0.385. So that actually tells you that brass is actually primarily copper. Brass is just it's an alloy of copper. Okay. So the units, the dimensional analysis, grams cancel, joules per gram, degrees C cancel, and you got degrees C. So that's cool. So let's do this problem. 300 times 4.184 times 1.1 divided by 53.5 divided by 0.375. And it looks like it's 68.8 degrees C. There's a minus that I even, you know, like talk all about this negative sign and then I forget to put it in there. There's a minus, right? Don't forget that minus. Now, what does that mean when delta T is minus? If delta T is positive, that means something got hotter, right? So with the water, it got hotter, so delta T was positive. If delta T is negative, that means it got colder, okay? So let's think about this. They didn't tell us anything about the temperatures of the brass, but we were able to find delta T of the brass, right? It's negative 68.8 degrees C. The question now is, what is delta T? Delta T is T final minus T initial, right? That's what delta T is, final minus initial temperatures. They didn't seem to give us any of them, but they actually did give us one. And the one they gave us is the final temperature. Because what they said was the final temperature of the water is 23.1, right? So the idea here is, well, why do you get into a hot bath? You get into a hot bath because you want to feel hotter, right? You want your skin to feel hotter. Feels nice, right? Blood flow and all that kind of stuff. So essentially the brass, whatever temperature it started off at, whether it was hot or cold or whatever, eventually it's going to have the same temperature as the water. Okay, now that might take 5 minutes. Metals conduct heat really well, so it probably only takes about a minute for that to happen, but eventually it's going to be at the same temperature. So the final temperature of the water is going to be equal to the final temperature of the brass. That's the key to these problems. So T final is equal to 23.1 degrees C. Once you've got that, finding the initial temperature, calculate TI of the brass sample. That's our question. Once you want to do that, that's easy, because now we know that negative 68.8 degrees C, that's delta T, is equal to 23.1 degrees C, that's T final, minus T initial. Okay, right? T final minus T initial is equal to delta T. That's all I did right there. So how do you figure out T initial? Well, what you could do is you could add T initial to both sides. So you'd have T initial. See, it's minus, so I'm adding it to both sides. So T initial minus 68.8 is equal to 23.1, right? I added it to both sides. Now I can add 68.8 to both sides. If you add this number to the left side, that becomes 0. If you add it to the right side, you get a big number. So what do we get? That looks like it's 91.9. And there you go. There's our answer. Essentially what happened was they put this piece of brass in the water. It was at 91.9 degrees C. It was hot, almost the boiling point of water. And then it transferred heat into the water, and the water got hotter and the brass got colder. Now notice the brass really cooled down quite a bit, right? It went from 91.9 all the way down to 23.1. That's a big change, 68.8 degrees C. So that really speaks to this issue of the specific heat capacity. The specific heat capacity is really how much heat something can absorb, but really not change temperature very much. So if something has a specific heat capacity, you could add a lot of heat, but it doesn't change temperature very much. It actually requires a lot of heat to get water to the point where it boils. In fact, it's such a huge amount, and of course water is useful for many reasons. It's such a huge amount that we use it to store energy. Right? It's actually used, what you do in a oil or coal-fired plant where you're trying to develop to get electricity, is you boil water. Water absorbs an enormous amount of energy, and then that water can turn a turbine because it's storing all of that energy. So the brass changes temperature with only a little bit of heat, but the temperature of the water doesn't change unless you add a lot of heat. So the water only changed by 1. Now there was also more water, right? 300 grams compared to 50. So the bigger the bath, the more heat you got to add to make it change temperature. But even so, that's a big difference in terms of how much their temperatures change. Brass changed by 68 degrees. The water only changed by 1 degree. Okay. All right, so that's a key problem right there. It's this one right here. Q of the material that you're adding to the water. Those two Q's, add them together, they're equal to 0. Substitute in the equations for Q, and then just solve for whichever one you want. Okay. And that pretty much does it for calorimetry. There aren't any other types of problems that we're going to do in that. And I want to point out that we did really, these were all constant pressure. We didn't do any constant volume. There are also constant volume ones. So when you deal with food calories, like food has a certain number of calories, that's really measured. The way they measure food calories is by doing a combustion reaction in what's called a bomb. And that's done at, not at constant pressure. It's done in a closed sealed container that's constant volume. So in that case, the way we calculate things would be different. But for this course, we're primarily focusing on constant pressure and heat at constant pressure. Okay. All right. So that wraps up all the calorimetry. Now there's one more topic left in this chapter. So what I'm going to do today is I'm going to show you that type of problem. So this is section 5.6, which is called standard heats of reaction. Okay. And you'll see this word as well, formation, standard heats of reaction or standard heats of formation, okay? So the idea here is that we have the ability now, having spoken about calorimetry, to imagine ways to measure energy changes. So you got this water bath, you got a thermometer in there, and then you could put a flask in here. And you could do a reaction, right? Let's try that a little bit better. Okay, so you could run a reaction inside here. It is useful for chemists and biologists and physicists and engineers to have a table of how much energy you can get out of a reaction. It's useful for many purposes, for different purposes, but essentially we want to have it just like we have a table of densities or a table of specific heats. We want to have a table of how much heat is released in chemical reactions. Okay, so this topic is all based on the idea that we want to have a table of heats of reaction for various chemical reactions. Okay, so for example, if I said the following, here's a reaction N2 gas plus 3H2 gas gives us 2NH3 gas. Suppose I'm studying that reaction and I want to really study the, what's happening chemically, physically, engineering. I might want to use it for engineering, right? So an interesting thing that's going on in engineering these days is that there appears to be a movement away from using what we call Freon, which are refrigerants that are used in air conditioning and refrigeration, and moving perhaps either to carbon dioxide or to ammonia, NH3. So people study these things in terms of their energetics. So we might want to look this up. Can we look up what delta H is for this table? I mean, for this reaction here. And it turns out you can figure out what delta H is just by looking that one up. And it turns out it's around 92 kilojoules. Okay, so for that reaction, the amount of heat you would get out. So if you had 1 mole, 3 moles of this, and you react them and you get 2 moles of that, the amount of energy, the amount of heat, the enthalpy change would be, it's exothermic, so it releases energy, releases heat, is 92 kilojoules, okay? So we want to look those things up. So the first step in kind of understanding how we're going to do this is that it turns out, how you balance the equation matters. We learned about that a little bit earlier when we first talked about enthalpy. If I wrote this equation like this, delta H is going to be different, right? Remember what we said? If you multiply an equation by some number, you multiply delta H by that same number. So I multiplied everything here by half. I took 1, turned it into, took 1, turned it into a half. I took 3, turned it into 3 halves. I took 2 and turned it into 1. So I multiplied it by half. So that means we would multiply negative 92 by half, and you get negative 46. Okay, so remember, the way we balance an equation is important. And the other thing that's important is the state of matter. It turns out that if you take liquid water and you convert it into gaseous water, that's called boiling, right? Vaporizing. There's a delta H associated with that, and it's 46 kilojoules. It's positive 46 kilojoules, okay? 44, sorry, 44 kilojoules. So the state of matter is important as well. So if we're looking at this being a gas versus a liquid, it's going to have a delta H value that's different. So we need to know what state of matter it is as well. So the first type of problem that you're going to do here, and that's really what we have time for today, we won't get into the calculations, is just how you write a formation equation. That's the first step. And here's how you do it. I'm going to show you an example. So we just want to write the equation for the formation of water in the liquid state. Okay, so I'm just going to write the formation equation. Now, when I say I write the formation equation, what I mean is I'm going to write a chemical equation. It does need to be balanced, but there's a couple of things that we have to be aware of. So it says to write the formation. So how do you do that? Well, it tells us to form water. So that's going to be our product. So whatever you're forming, that's the product. It said what the state of the matter was. It said liquid. So I'm going to write it this way. Okay. So then you go back and you say, okay, well, how do I figure out how to make water? How do you make water? For these problems, what you do is you look at the elements that are in the substance you're making. So in this case, it's water. What elements are in it? Hydrogen, right? There's hydrogen in there. And then there's also oxygen in there, right? So there's two elements. So what you do is you write those elements down. Now, if you recall at the beginning of the semester when we were doing chapter 3, one of the things I mentioned was that there's 7 elements that are diatomic. Let's go back to that, right? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, right? Those are the 7 diatomic elements. So if we are writing this equation, we have to use the correct formula for these elements. So if it's hydrogen and oxygen, those are diatomic, right? So I got to write it as H2 and I got to write it as O2. Okay. It's as simple as that. You look at what they're trying to form, you write the formula as a product, the state of matter is given, and then you just figure out which elements are in it just by looking at the formula, and you write it as a reaction, the first element plus the second element. Then you have to balance it. And now here's where you have to be careful. When you balance it, you want to have 1 mole of the product. So that limits how you can balance it. You can't have 2 moles of the product or 3 moles. It's got to be 1 mole. So how do we do that? Well, that means we can't change the coefficient in front of the water. It's got to be a 1. All right. So what you do is you say this. You got to use fractions. You say, okay, hydrogen, we've got 2. Hydrogen, we've got 2. So that's cool. Hydrogen's done. It's balanced. But the oxygen, we have 2 here. We only have 1 here. So you might have learned the balanced equations by putting a 2 in front of the water, but we can't do that because we want to keep the coefficient as a 1. And so what do? You write this half here. A half times 2 is equal to 1. So when you do these problems, these reactions of formation, and it says to write the equation, you're going to possibly have fractions on the reactant side for 1 or more of the elements. I actually showed you another one, right? 1/2, 3/2 right there. But the coefficient on the product side's got to be 1. Okay, can't be a half, can't be 2, it's got to be 1. The reason for this is because when we produce tables of these delta H's, we want to have it done in a very standard way. And the standard way is to have the 1 mole of the product. We just want to have 1 mole. So whenever you look these values up in a table, and we'll talk about the tables tomorrow, every time you look up a value in the table, it's going to be assumed, oh, that's 1 mole of that substance, not 2 moles, right? So we wouldn't want to have a table for 2 moles and then for another material have a table for 1 mole, right? You want everything in the table should be for 1 mole. So to make that happen, when you balance the equation, you sometimes have to have fractions on the reactant side, okay? Let me show you one more. Okay, so write the balanced chemical equation for standard formation of gaseous nitrogen monoxide, which is NO. Okay, so let's take a look at that one. So again, you're forming nitrogen monoxide. It's also gaseous. It's telling you it's a gas. So 1 mole of NO, and then it's gas. Now we go back and we say, okay, well, what elements are in NO? There's nitrogen in it and there's oxygen in it. So nitrogen plus oxygen. Okay. The next thing we do is we say, okay, are these one of the diatomics? Are they? Yeah, they are actually. Nitrogen and oxygen are both diatomics. If it was phosphorus, you just put P. You don't have to do P2. If it was sodium, you just do Na. You don't have to do Na2 or anything, right? It's just those 7. But a lot of the problems we do involve those diatomics. So it's 2. Okay. Then the last step, or the next step, is what you do is you balance it. But remember, we can't change the coefficient on the product side. We can only change it on the reactant side. So that means we're probably going to have fractions if it's a diatomic. So we want 1 nitrogen, so you put a half, right? A half times 2 is 1. We want 1 oxygen, a half times 2 is 1. And there you go. So it's balanced. One more step, which is the states of matter. So let me point out these elements. H2, N2, O2, F2, Cl2. Those are the first 5 of the diatomics. Those are all gases. Br2 is a liquid. I2 is a solid. Okay? All metals are solids. With one exception, you know that exception, right? It's mercury. Mercury is a liquid. So except for mercury. It's a liquid, okay? So, and then what about the other nonmetals? The other nonmetals. So what are the other nonmetals? P, S, Se, right? As, those are your nonmetals. They're solids. Okay, so these 5 are gases. Bromine is a liquid. Iodine is a solid. All the metals are solids except for mercury. And then all the other nonmetals are solids as well. So the only ones that are gases are these ones right here. And the only ones that are liquid, there's actually only 2 elements in the periodic table that are liquid at room temperature. Those ones will be liquid. So that means we're going to put a gas and we're going to put a gas, right? Those 2 elements are in that list of gases. Okay. Noble gases, don't need to worry about them because they're not going to be involved in chemical reactions. So helium, neon, argon, don't worry about those. Okay. So there you go. So tomorrow, what we'll do is we'll look at how we use these standard equations of formation to do calculations. And that's actually, it's a pretty simple calculation. So we'll do that. That's the end of chapter 5. And then our next topic is chapter 10. So we'll get started on that. We'll start looking at pressure of gases tomorrow, and that'll get us started on chapter 10. Okay. So have a great day. Reach out to me if you have any questions. And I hope everything's going well.
Thank you.
Thank you, Professor.
Bye-bye.